Okay, folks, welcome to the second batch of carbonyls. I know you're excited. I'm excited to tell you about them, and I know that you're excited to learn about them. So in the last lecture module, we talked about everything there was to know, pretty much, about type 1 carbonyls. But at that point in time, I told you that we're actually going to break this up into two sections, and the second section is going to be type 2 carbonyls. We're not very creative, folks. We're organic chemists. We're organic chemistry. It's not rocket science. It's never creative. So type 1 and type 2, group 1 and group 2, whatever you want to call it, it doesn't matter. So with type 1, think about all of those functional groups that you talked about. Acids, carboxylic acids, anhydrides, all of the mess of the functional groups that came around one after another, and we had to learn how to name every one of them, like the esters, the amides. Well, good news here, folks. In type 2, there's just two. Type 2 carbonyls have two functional groups that we're going to learn how to name and that we're going to be introduced to. And this is an aldehyde and a ketone. And both of these you have seen before. So an aldehyde functional group is a carbonyl because all of these are carbonyls. It's type 2 carbonyls. So it's a carbonyl, and the aldehyde has a hydrogen at the end of the name or the structure. The ketone group is the C double bond O, and then on each side of the carbon, we have some other type of alkyl group, another carbon chain, a ring, it can be anything it wants to be. So that's the major difference between the aldehyde and the ketone. The aldehyde has a hydrogen on one side, and the ketone, well, there's no hydrogen there. It's both carbons flanked on each side. So the aldehyde and the ketone, we're going to do something very similar that we did in type 1. We're going to learn how to name these, and then after we name them, we're going to learn how to do reactions with them. All right, that's pretty much what we're going to do. Now, I'm going to say this is kind of simple, right? It's pretty much all that we're going to do. Name an aldehyde, name a ketone, learn how to do reactions, blah, 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 blah. But there's actually more to the story. And the reason is because there's actually more that's included in the lecture. Look at this lineup, folks. Look at this lineup. So the only thing that I've really talked about at this point is number 1 and number 2, nomenclature of aldehydes and nomenclature of ketones. But now that we're finished with the carbonyls, there's actually more functional groups and different types of nomenclature that we can introduce. And this is with molecules that have multiple functional groups now. We never really have talked about this, right? It's always, this has a carboxylic acid. How do we name that carboxylic acid? Well, what if it has a carboxylic acid and an aldehyde? That's a possibility. It can have both. So how do we handle that type of situation? How do we name those types of molecules? Do we name it as a carboxylic acid or do we name it as an aldehyde? So if there's multiple functional groups, we're going to have to learn how to name those, and that's step number 3. Step number 4, reaction with Grignards all over again. Wouldn't you know? That ties us all the way back to the very beginning of the semester. Number 5, reactions with acetylide. Do you remember what acetylide was? I hope so, because if you had me for Chem 251, we used the acetylide ion to elongate a chain. And that's now coming back. Number 6, reactions with hydrides. Well, what is a hydride? Well, that you're going to learn about because we're going to do some reactions with them. Number 7, reactions with cyanide. Don't make me in the room. See you later if you're going to be using cyanide. Bye-bye. But we're going to talk about them at least. Number 8, reactions with amines. So we've talked a little bit about amides and those reactions, and we'll talk about a little bit of amines as well. And then number 9 is pretty special. Number 9 is a fancy little reaction that's called the Wolff-Kishner reduction. And that Wolff-Kishner reduction is pretty important because it was named after some people that kind of discovered it. So whenever we see these specialized reactions, we want to take note because we're going to have to figure out how they work. There's something special about them, and we have to kind of give credit where credit's due. Number 10, reactions with water, again. Number 11, reactions with alcohols, again. And number 12, another one, Wittig. What is a Wittig reaction? Well, once again, you'll figure that out when we get to that point. So, when I say type 2, it's just a little O aldehyde and it's just a little O ketone. Well, number 1 through number 12 is kind of giving you a different story with that. Now, I first want to go back and tell you that you have been introduced to aldehyde and ketone before. Again, if you've had me for Chem 251, I definitely know that you've been introduced to this. And the reason that you've been introduced to it is because there was a moment in Chemistry 251, Organic 1, that we talked about alkynes. An alkyne is a C triple bond C. I hope you remembered that. So in these alkyne reactions, we could add water in the presence of acid to these molecules. And do you remember what happened? Well, the triple bond broke and two sides of attachment open up. All right, so here's my triple bond. And that triple bond is going to react with this water. Now, keep in mind, back in the day, I told you, write water as HOH. That will help you because you're going to break that up into two halves, an H and an OH piece. So back in the day of Organic 1, you that double triple bond to make a double, and two sides of attachment open up here and here, and hydrogen goes on one side, and the OH from the water goes on the other. That's kind of how I told you to think about these reactions. Well, the reason that I'm bringing this up is because this was a special type of functional group. This was a double bond between the carbons with an OH, and this was called an enol. And if you remember Chemistry 251, enols, folks, were not very stable. We went through the process and said, whoa, 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 it actually is going to rearrange on us. This is not the final product of these reactions. What happens is that oxygen comes in and it's real electronegative, and it wants those electrons and it wants to suck those electrons up. I mean, that's what it does. So that electronegative oxygen is going to persuade the electrons to move to the oxygen side of the house. So what happens is that the double bond that was here between the two carbons actually gets moved up between the carbon and the oxygen. And oxygen says, ha ha, I've got what I want. Thank you for giving me your money. Now I'm going to go shopping. Well, that oxygen's got to get rid of something. It has a hydrogen, it has a bond, it already has two bonds, right? So if we're going to put in another bond between the carbon and the oxygen, that would make three. So this oxygen, it's got to get rid of the hydrogen. And really what happens here is that the double bond moves up, almost like delocalization here. And the hydrogen will switch over and satisfy that carbon when that double bond breaks. So we have a hydrogen shift pretty much, and a double bond shift. And depending on what type of compound that was here, right? If there was another carbon on this side, then folks, there was a carbon there. And look at this. This was the ketone that we talked about during that time. Now, if the carbon, double bond carbon, has an oxygen, an OH, and we see some rearrangement, and on the other side of that carbon we have a hydrogen. Folks, this is our aldehyde group. So we've already been exposed to aldehydes and ketones. We've already kind of done one reaction in order to make the aldehydes and ketones, and all of these are fair game. So the alkynes can react with water in the presence of acid. That's just one form of the reaction that can go forward in order to form an enol, and that enol will rearrange in a tautomer. That was a fancy word that we learned, right? Tautomer. And then that could give us a ketone or an aldehyde, depending on where that OH group and that double bond was located. All right. So there were some other reactions that we did back in the time. I would tell you to go back and look at these, right? We also talked about a mercury version. This mercury version was very similar to water and acid. And we also talked about BH3 and THF. That was an anti-Makovnikov reaction that I called Marky Mark. And that was also fair game. And that was also special because that put the OH groups in the opposite positions. It was one of the ways that we were able to get the OH group on the end. And if it's on the end, then this is going to give me an aldehyde for sure. So this borane THF forms aldehydes. And all of the other water additions, the mercuric additions, and so forth will tend to give me the ketones. And all of this was review. All of this is assumed. I know that's a big, big word, but it's assumed that you should know these types of topics at this point. All right, so I just wanted to touch base with that just a little bit before we go further into the type 2 carbonyls. All right, so let's just start with our nomenclature section of aldehydes and ketones. And you're going to see that this is pretty simple. There's no really big difference than what we've been doing so far. And I first want to talk about the aldehyde. All right, so if I have an aldehyde, a carbon double bond O with a hydrogen, and on this side we have something. All right, well, let's just put another carbon there. We'll keep it simple. No big deal. So I need to figure out how to name this, and just like before, we're going to name this using IUPAC rules, and we're going to name this using common nomenclature. So I've got to figure out, okay, well, how would I kind of tell you that this thing is an aldehyde without drawing the structure, just giving you the name for it? Well, once again, I told you organic chemists are not very creative. So what they use is they use part of the name of the aldehyde. And if you look at aldehyde, it starts with AL, doesn't it? Okay, well, it better be in the name. If I'm going to name it as an aldehyde, that AL better be in the name some form, some fashion. And this is how we do it. Find the longest carbon chain. Okay, 1 and a 2. So we name this ethane. All right, well, like all of the other times that we've named anything at all in organic chemistry, if you've paid attention for 2 semesters now, I think that you know what I'm going to get ready to do. Whoop! Get rid of the E. And then we're going to change that E into a modified ending. I'm naming it as an aldehyde. There is an aldehyde functional group. Aldehyde functional groups start with AL, so I'm going to use AL as the ending of the name. So the IUPAC name for that structure is ethanol. Go figure. I told you this wasn't very hard. If you've been paying attention, especially in the carbonyl family, folks, it's the same stuff. It's just learning what to change. The really, really tiny modification that we have to do to make this thing work. That's all we got to do. Common name. How do you think we're going to common name it? Well, we common name a 2-carbon chain. What do you think it's going to be called? All the other times, what do we use? 2 carbons? This is an aceta or acete. A-C-E-T. And in the common nomenclature, we've got to tell you it's an aldehyde somehow. And common nomenclature just says, well, whatever. Let's just use the word aldehyde. So this is called acetaldehyde or acetylide. All right, so ethanol and acetaldehyde or acetaldehyde. Some people say acidaldehyde. I don't really like to say acidaldehyde because it sounds like I'm saying acid, A-C-I-D, and there's no acid involved, but that's what some people do. It just rolls off the tongue that way. Okay, so nothing surprising, nothing fancy, nothing new except the addition of the AL at the end. Okay, well, what's special about this? Nothing special about it. All right. Well, folks, let's do some more examples. You on a roll? Let's see. Let's do a C double bond O with an H on this side and an H over here. Name it. Name it both ways. Okay. Well, IUPAC it. There's a 1-carbon main chain. Methane, M-E-T-H-A-N. Drop the E, add A-L, methanol. Good. That's all you've got to do. All right, we're going to do common names next, back to back to back. So I'm going to move on to the next structure. And let's do a C double bond O with an H. And then here, let's do a CH and a CH3. And let's put a BR right here. Name it. Okay, IUPAC. Find the longest carbon chain. All right, 1 and 2 and 3. So this is a propane. Drop the E and add a L. I'm done. Wrong. No, you're not done. There's something else here that you have to kind of keep in mind. Look, there's a bromo right there. We got to name the bromo group. How are you going to name the bromo group? Okay, well, on carbon number 1 and carbon number 2 and carbon number 3. At carbon number 2, I have a bromo group. So 2-bromo propanol. There you go. There's the full IUPAC name for that structure. Is that hard? I hope it's not. Again, it's all a review, folks. That's all that it is really at this point. Okay, so let's keep it going. Let's do some more examples. Let's do a C double bond O with an H. And then on this side, let's do a CH2 and a CH and a Cl and a CH3. All right. IUPAC it. And a 1, and a 2, and a 3, and a 4. 4 is the longest carbon chain. All right, so on carbon number 3, I have a chloro group. And then this is a 4-carbon chain, which is a butane. Drop the E, add a L. There you go, 3-chlorobutanol. All right, let's do another one. C, double bond O, H. And we'll do a CH2, and a CH, and a CH3, and let's do a CH3 down here. Okay. So 1 and a 2 and a 3 and a 4. 4 is the longest carbon chain no matter how you see it. 4. And on carbon number 3, goodness gracious, why is he doing this to me again, right? On carbon number 3, there is a methyl group, and there is a 4-carbon long chain. Drop the E and add a L. 3-methylbutanol. And we'll do one more. And this one, we'll do a C double bond OH. And I'll do 1, 2, 3, 4, 5. And then carbon double bond O with an H. All right, so 1, 2, 3, 4, 5, and 6. There are 6 carbons in total here. All right, there's 1 carbon. There's my 2nd. There's my 3rd. There's my 4th. There's my 5th. And there's my 6th. Okay, so the problem here is that there's 2 aldehyde groups, and that's okay. And you're probably thinking, well, wait a minute, you're skipping steps on me. This was like step number 3. You said multiple groups, right? Well, it's different groups for step number 3. This is the same. There's 2 aldehyde groups. So we use the rules for IUPAC that we've always had at this point. So 6-carbon chain is called a hexane, right? So hexane, drop the E and add AL. However, in this case, there's 2 AL groups. So I don't want to call it hexanal-al. I mean, think about how silly that is. Sounded out loud. Hexanal-al? No, I'm not going to name it hexanal-al. So instead, I'm going to name it a hexane. And I'm going to erase this just to give me a little bit more room. And the reason I keep the E is because what comes next is a di for 2 and then al. Hexane dial. So that sounds almost as silly as hexane al does, but hexane dial maybe is a little bit better and it doesn't make you sound a little crazy. All right, so hexane dial, if that E was not there, I would give you credit for it. It's not a big deal. But the reason that they put the E there is because they do not like to see the N and the D side by side. It looks weird on a sheet of paper. So they include the whole word hexane for that reason. If you want to drop the E to be consistent with it, then drop the E, whatever. I know what you mean by it. I'm going to give you credit, whatever. But that is the reason that they keep the E in the name. All right, so here are multiple examples. Each one of them are aldehydes, and this is how we IUPAC those names. Now, let's go through and common name them. All right, so methanol. Word for a one-carbon chain is form, right? I mean, the formic and the acetic and the propionic, the butyric, the valeric, the caproic, all of those are what I'm referring to, just like before. So a common name, one carbon, is form. And then we add the word aldehyde. Folks, there's your structure for formaldehyde. That's what that is. Look at that. You were able to draw the structure from the name, and now you'll know what that structure is just by hearing the word formaldehyde at this point. That's all that it is. The name is a dead giveaway of the structure. All right, let's look down here at this next one that we did. How do we common name this? Okay, well, 3 carbons. Name of a 3-carbon chain is going to be propion. So P-R-O-P-I-O-N. And this is aldehyde at the end of it. Propion aldehyde. Okay, but we have that bromo group, right? So how do we name that bromo group? Well, we don't use the 2. Because 2 is really for IUPAC, not for common. And instead, this is where we use the Greek alphabet. So remember, this carbon in common nomenclature doesn't count. That is the word aldehyde right there. So this is my alpha carbon, and this is my beta carbon. So this is going to be an alpha bromo propion aldehyde. And that is the common name for that structure. All right, well, let's look over here to the right. Same kind of thing here. If I need to common name it, 1, 2, 3, 4. This is a butyr. B-U-T-Y-R. That is the prefix that we used every single time so far. We're going to add the word aldehyde on the end, butyraldehyde. And that butyraldehyde, 1, 2, 3. Numbers are only for IUPAC. So this carbon is the aldehyde carbon. So that means that this is alpha, this is beta, this is gamma. So this is a beta chlorobutyraldehyde. Next one down here. 1, 2, 3, 4. Another one. Yes, butyraldehyde. There you go. And on this one, we have alpha and a beta and a gamma. So beta has a methyl group. So beta methyl. If you give me this, that's perfectly fine. I'll take it. But there is another one. There is another one. What do you mean there's another one? Okay, well, see the CH3CH3CH? Folks, this is an iso group right here. We're doing common names. If this happens at the end like this, we can call it an iso something if it's a clean structure, nothing else on it, nothing crazy happening, and there's not. It's just carbons and hydrogens with the aldehyde group. That's all there is. So if I wanted to give you another common name, that's perfectly fine. Well, number of carbons in total, 1, 2, 3, 4, and 5. So I could call this a isovaler aldehyde. Valer is the 5-carbon word. So isovaleraldehyde. That's all there is. This one down here at the bottom, no common name at all for this one, because there's no way that I can common name 2 groups, folks. That's it. No more that I can do with that structure. All right. One more thing that we want to do before we stop the video is talk about aldehyde groups on a ring. All right, so here's a ring, And let's put a C double bond OH on here, and maybe a CH3 on here, and figure out how to name it. Just like before, we name the ring as a whole name. I mean, this doesn't really change. So this is a cyclohexane. We do not modify any of those endings. Cyclohexane, that's what it is. Well, in order to name this on a ring like this, for IUPAC purposes, that C double bond OH, that is an aldehyde, I know that. But we often always put the word carb in front of it. So this is a carbaldehyde. So this is something that isn't new. It's something that we did with all of the other functional groups back in the day. We always modified that particular type of ending to kind of keep in mind that is directly attached to the ring structure that I've labeled in front. So cyclohexane carbaldehyde is how we would handle this with IUPAC. Now, if this is the aldehyde group, then that means that this is kind of like my first carbon. And on my second carbon, I see this methyl group there. So 2-methyl cyclohexane carbaldehyde. Now, that is the IUPAC name for that structure. Now, it's not pretty. It's probably not easy. Once again, ring structures get most people every single time anyway, but that is how we name it using IUPAC rules. Something else that I want to also keep in mind, kind of go back in the day of Chemistry 251, and let's shade this one in, and then let's do a dashed wedge here. Well, the way that we would handle this, they're trying to tell me a little bit about stereochemistry. One is pointed toward me, and this is the solid wedge, and one is pointed away from you, and that is the dashed wedge. So if they're pointed in opposite directions, they want me to include that stereochemistry in the name, and I can do that simply by putting the word cis or trans in front of the name here. And this is trans because they are in opposite directions. The cis would be on the same side. So in other words, if both of those were solid wedges, or if both of those were dashed wedges, then this is the cis form of that particular type of molecule. All right, and we'll do one more. We're almost done. Not yet, not yet. I'm not ready with you yet. Okay, so here we'll do a benzene, because we know all about benzenes now. We learned something this semester. Well, if I wanted to IUPAC this structure, I do the same thing. I write the word benzene, and then this is carb, and then I write the word aldehyde. So benzene carbaldehyde, there we go. But you know a common name for this structure. We learned a common name for this structure. You were supposed to learn a common name for this structure. So what did we call a benzene ring with a C double bond OH on it? Well, we called it benzaldehyde. Oh, I see now. So this is a structure that does have a common name. This common name we use very, very often. And that is why we call this by the common name versus something like the previous example that we did. That was just a ring. There was nothing special about it. It's not very common. We don't use it in the lab very often, but this one we kind of do. So benzaldehyde, there you go. A beautiful little molecule that smells like cherries. If you buy a jar of machino cherries in the grocery store and pop that bad baby open and take a big, big sniff, that's exactly what benzaldehyde smells like. All right, so there is two examples of how to use IUPAC and common nomenclature when aldehydes are connected to ring systems. All right? Okay, so that's where I'm going to stop. In the next video, we'll continue on. We've got ketones to go through. We've got multiple functional groups to go through, and we'll keep trucking on in the next video when you come back.